Okay, so in the next question, we're looking at an entropy question here, and balancing entropy and enthalpy to work out what's happening to the total entropy of a reaction. So the reaction that we're looking at is this one here. So we've got an alkene reacting with carbon monoxide and water to make a carboxylic acid. Right, so the enthalpy of formation data is given in the table. Okay, so the enthalpy of formation data you just get from your data booklet. And the entropy data is given in the table. Again, you just get that from your booklet. The first part of the question is asking you to calculate the standard enthalpy change for the reaction. To calculate any standard enthalpy change, the easiest way of doing it is to do products minus reactants. You could do a Hess cycle here, but obviously that's just slightly more complicated. So I've got the sum of the products. Well, in this case, I've only got one product, it's my carboxylic acid, minus the sum of the reactants. Okay, you need to note that the enthalpy of formation is obviously per mole. Because of the definition of enthalpy of formation, it's the energy required to form 1 mole of compound. Well, in this case, I've got 2 moles of my carbon monoxide and 2 moles of water. So those enthalpy values need to be multiplied by 2. So that gives me a final sum of minus 994.3 minus plus 109.9 for the enthalpy of the formation of the alkene, plus 2 times minus 110.5 for the enthalpy of formation of carbon monoxide. Remember, there's 2 moles of carbon monoxide, plus 2 times minus 285.8 for the enthalpy of formation of the water. Remember, there's 2 moles in the enthalpy of 2 moles of water being used. And that overall, when I do that sum, gives me an answer of minus 311.6. Okay, so again, there's 2 marks for plugging in your values correctly. 1 mark for using the fact that you've got delta HF is equal to the enthalpy of products minus the enthalpy of reactants. And 1 mark for remembering to multiply your carbon monoxide by 2 and your water by 2. Okay. Again, I'm just going to do exactly the same to calculate the entropy of the system. Again, I need to work entropy of formation is per mole. So again, I need to multiply the carbon monoxide value by 2 and the water value by 2. And this gives me an entropy of the system of minus 563.7 joules per mole per Kelvin. Now the next thing you need to notice is that your entropy value is in joules and your enthalpy value is in kilojoules. So when I'm calculating my entropy of the surroundings, I'm going to use the equation negative delta H over T, but I need to convert my kilojoules into joules by timesing by 1,000. So I've got minus of minus 311.6 times 1,000 divided by 298, which gives me plus 1045.6 joules per Kelvin per mole. Okay, I know that my entropy of the system is minus 563.7. So my total entropy is just the sum of those two, which is plus 481.9 joules per Kelvin per mole. So again, I'm getting 1 mark for my equation, 1 mark for remembering to multiply it by 1,000, and 1 mark for my total entropy calculation. In the second step, or the next question rather, it's asking you to explain whether decreasing the temperature is going to increase the entropy of the reaction. So those of you who talks about Gibbs, it's not going to be relevant, it's not going to be helpful in this case, because it's not asking you to calculate the impact on Gibbs, it's asking you to calculate the impact on the entropy of the system, the entropy of the surroundings, and the total entropy. Okay, so the entropy of the system is just products minus reactants. So it's not dependent on the temperature. So the entropy of the system is not going to change. The entropy of surroundings is delta minus delta H over T. So as I decrease temperature, that means that denominator is getting smaller. And therefore the entropy of the surroundings is getting bigger. And therefore the total entropy is going to be larger because a bigger number plus no change makes a bigger number. So therefore the entropy total is going to be larger. So the statement is correct. In the next question, you are just looking at which bonds were diminishing. Now, in this case, I didn't give you the data booklet, if you remember, so I wasn't interested in what the particular values were or the wave numbers were. I was just interested in which peaks were going to disappear. So, you're comparing your alkene reagent with your carboxylic acid product. So the peaks that you can get are either the OH of your carboxylic acid or the CO of the carboxylic acid. They are going to appear. You are going to still get the CH of an alkane chain in your carboxylic acid, but you won't get the CH of the alkene chain. So that is going to disappear. You also won't get the carbon-carbon double bond. So that is going to disappear. Okay? And the final question, what's the taste going to be like? It's going to taste sour.